Welcome back, folks. Hopefully you had a little bit of a good break, and you might be seeing this over the break. What we're going to talk about for the first part of this semester is heat and heat transfer. And we're picking up with the idea of energy that we ended up the first semester with, and conservation of energy and things of that nature. And those same rules still apply here. So what we're going to talk about, we're going to first off figure out what we mean by heat and heat transfer, because these ideas, you may have had them in chemistry, but we need to be a little bit more specific about what we're talking about. And from our definition point of view, we get into this idea of temperature, okay? Temperature is a measure of the average kinetic energy of the particles in a substance, okay? Kinetic energy is what? The energy of movement, okay? So the particles inside those objects are moving, the molecules. There's something called internal energy, which is U, which the total amount of energy is associated with atomic motion. It's proportional to the temperature. Most of the time we'll be using that one, okay? If an object seems hot, that means the particle motion is fast or has a high U. If it's cold, I'm putting those in quotes because those are interesting. Okay, you'll have slow motion. Okay, you can kind of think of it if you've ever, even on a lighter. If you try to light a lighter on a cold day, okay, the molecules in there are moving slow, and it's harder to light. If that lighter is a little bit warmer, you'll see the flame get higher. You'll also see it since it's wintertime. Sometimes when it's really cold, you'll see the tires on your car go down a little bit. Why? Those molecules aren't moving as fast as they were. Okay? So on a cold day, if you leave your car out overnight or leave it out for a couple of days, it may appear like a tire or two is flat. It's simply because the molecules inside there are going a little slower. Okay? This is where we get into, this is one of the most important definitions we'll have right here, this idea of heat. Heat is the transfer of energy due to a difference in temperature, period. Don't tell me heat is how hot something is, how cold something is. Okay? Something feels hot or feels cold because of this transfer of energy. Okay? If you put an ice cube in your hand, okay, it feels like it's cold because the heat is leaving your hand and going into the ice cube. Okay? Does that make sense? Kind of like a hot cup of coffee, okay? Or a hot cup of hot cocoa. That cup feels warm, okay, because it's transferring the energy to your fingers. Okay? So if something, remember, temperature is the average kinetic energy of the particles in an object, okay? When you come in contact with other objects that feel hot or feel cold, well, there's transfer of energy going on. Okay? This kinetic molecular theory, you probably had it back last year in chemistry. Simply the particles, the faster the particles move, the greater kinetic energy, or the greater thermal energy, right? You remember from our kinetic energy formula before was 1/2 mv squared, where v was the velocity, okay? So that, what was true of cars and roller coasters and things is also true of the molecules inside a substance. Now, this idea of thermal equilibrium we've just brought up, putting an ice cube in your hand or holding on to a hot cup of cocoa. Thermal equilibrium is the state where two objects in contact with each other in some way, shape, or form have the same temperature. And on that, energy always travels from an area of higher energy to an area of lower energy. When in doubt, guess high to low. Okay? It's the same way with pressure. It's the same way with a lot of things. Remember back diffusion and osmosis and things like that back in biology, okay? Concentrations move from high concentration to low concentration. Well, heat does the same thing. If you have a fireplace in your house because your power went out like it did before, that area next to the hearth is nice and warm, okay? Go on the other side of the room, it's going to take a while to heat up. Scales of measurement, you've already seen this. You'll see us with degrees C, base where water freezes at 0. Water boils at 100. You might see us also use the Kelvin scale. This is an absolute scale, which is based upon the movement of particles alone. Okay? So what happens? At 0 Kelvin, particle movement has stopped. I don't think experimentally we've gotten ever to that point. We've gotten to within, if I remember, I'm trying to remember the research, but I think we've gotten to like within 1/10 of a degree. But it's, you know, once particle motion stops, you know, things could get interesting. Okay, so 0K is minus 273. That should be a degree sign. I don't know what happened to that one. Minus 273 degrees C. Okay, you'll have to watch your units on this, simply because when we get into calculations later on, you'll have to look and see whether or not your constants are in Kelvin or in Celsius. Another thing that comes up quite a bit is this idea of specific heat. Okay, it's the amount of energy that must be added to a material to raise the temperature of 1 gram 1 degree. Okay, this is a character of whatever substance you're looking at. Okay, each material has its own specific heat. It doesn't change. Okay, there'll be 2 different types of units. Sometimes you'll see joules, kilograms, Kelvin, joules per kilograms Kelvin, or you'll look at joules per kilogram degree C. Okay, and if we want to calculate, this comes into a calculation. This C here is in temperature. This is the specific heat. Okay, you'll sometimes see me refer to it as specific heat capacity. Okay, but it's specific heat. So it's basically mass. The amount of energy in the system is the mass times the specific heat times this change in temperature. And this will actually be a change in changing Q there, because energy is going to be lost or gained. We'll get into some calculations a little bit more. But this specific heat capacity measures the amount of energy that has to be added to a material to raise the temperature. Okay? Water has a very high specific heat. Well, if it has a high specific heat, does it heat up slowly, or does it take a long time to heat up? Well, if you have a low specific heat capacity, that means that it doesn't take much energy to change your temperature. Okay? If you have a high specific heat capacity, it takes a lot of energy to raise your temperature. Okay? And that's what water is. Water is a great thermal blanket, you know, in the oceans. Okay? It takes a lot of energy. It absorbs a lot of energy without changing temperature. Okay? If you go to the beach, the air outside might be nice and warm, or even the sand will get good and hot, but the water doesn't change much. Then when the sun goes down, what happens? The air cools off, right? So the air and the sand will change, but the water will stay basically the same temperature all day. There's something also just called heat capacity instead of specific heat capacity. Okay, the amount of energy that must be added to change the temperature of an object. See the difference? Okay, so sometimes in your calculations, and I'm going to have to be sure to go over this in class, whether it's heat capacity times the change in temperature, right? Our mass has gone away here, folks. okay? And we'll use, our change in heat will be calories or joules. Um, and what we'll end up doing, again, you'll have to watch uh, your units, okay? Where your change in temperature, remember your change in temper is always going to be final minus initial, okay? Can you have a negative Q? Yeah. Negative Q means you just lost heat. Positive Q means heat is gained, okay? So if you look back over what we need to know about this, you need to understand what heat is, what temperature is, okay? And basically we'll get into in a little bit this law of conservation of energy, which we talked about, that energy is neither created or destroyed, okay? I'm going to break this into two different segments because I think this file's getting real big if I keep on going. So I'm going to stop this puppy and I'm going to save this one and then I'll do heat 2, okay? So there'll be another short video. I'd rather have two short videos than a long one because these files get kind of large, okay? But what we're talking about, you know, this heat energy, we'll get into the calculations in a little bit, okay? Negative Q, you lost heat. Positive Q, heat's gained. What do you think's going to happen? You know, what happens when you put ice in hot tea? Eventually, everything comes to the same temperature. Okay, but we're going to get into that in a minute. Let me save this puppy, and then we'll be right back.